Hello sailors, I'm Captain Tom Tursi from the Maryland School of Sailing and Seamanship. This video demonstrates the detailed calculations needed to convert a celestial shot of the sun into a line of position for your navigation plotting sheet. It follows a sample problem contained in our Celestial Navigation for Sailors textbook, and it provides detailed step-by-step descriptions and graphics illustrating the process. I hope you enjoy it, and I hope you find it helpful for your future navigation at sea. Let's take a look.
Okay, now let's talk about the calculations. What you've done so far is that you took your shot, you recorded the data on your voice recorder, and the next step is to take that data and transfer it to your logbook. And I'll show you how that looks in a handwritten logbook. First off, like this. Basically everything that you need to do the calculation is shown on this page. The data and the site reduction, and at the bottom we have the results of those calculations. And here is a smooth copy of that. Let's go through the sections of this. First off, at the top, in this top box above the first red line, we have the data. November 5th, 93, the sun, the lower limb. It could be upper limb, but this shot was the lower limb. We have the index error, the watch error, and the height of eye, which I call my 3 E's. And then over here we have my 3 L's, that is the dead reckoning latitude, dead reckoning longitude, the distance log reading, and then we also have the air temperature and the barometer pressure. And then below that we see the time in zone time, 08:28:39. And then we also see the sextant altitude that we just shot, 27 degrees, 15.9. And then the other sections here, this next section below that are corrections to the data, where we're going to convert time to Greenwich time, where we're going to take the sextant altitude and convert it with some corrections to observed altitude, HO. And the next section is where we compute the ground position of the sun at that moment in time. And you see that's in 2 dimensions. One is GHA, Greenwich hour angle, and the other is declination, that is the position of the GP of the sun either north or south of the equator. In this case it's south of the equator. And the next section is where we assign an assumed longitude and an assumed latitude, and we compute the LHA, that is the local hour angle. And then the next section is where we calculate the HC, that is the computed altitude, and the ZN. And then the last section is calculating the intercept, the length of the intercept. So we'll take each of those sections one at a time and go through them in some detail. So let's look here in the text. So let's take the first item, corrected zone time. So what we have to do at the time, we took a shot in ZT, and the ZT is referring to the 15-degree segments of the Earth longitude. Remember, 360 degrees divided by 24 hours gives you 15 degrees per time zone. So what is shown here in paragraph number 2 is apply the watch correction that we observed over the single sideband radio. So we have to apply the watch correction, and in our data we see that the watch error was 1 second fast. In other words, our wristwatch was 1 second ahead of Greenwich. So going back here then, we have a watch error which is fast, so therefore we're going to subtract it from the zone time. And the zone time was 08:28:39, and therefore we're going to subtract that 1 second from the 08:28:39 and get a corrected zone time of 08:28:38. And then our next step is to calculate the Greenwich Mean Time, and there's a couple of steps to that. the first thing we have to do is take our longitude, our DR longitude, and let's look at that. Here's a sample problem. Our DR longitude was 68 degrees 59.0 minutes west. So with that in mind, we're going to take 68 degrees 59.0, and we're going to be dividing this by 15 degrees per hour in order to compute hours. So we have to first convert the 59.0 minutes to decimal degrees to allow us to divide. So we take the 59.0 minutes, divide by 60 minutes, and that comes out to 68.98 degrees west. We're going to take that number then and divide it by 15 degrees, and this is really degrees per hour, and that gives me 4.6 hours west of Greenwich. So we are in the time zone number 5 west, and we get that by looking at this 4.6 hours that we're west of Greenwich, and that's based on the Earth rotation at 15 degrees per hour. So what we're going to do to determine the time zone is to round that up, since it's more than 4.5 hours, 4.5 hours. So we're going to round up. If it was less than 4.5 hours, like 4.49999, we would round down to zone 4. That is shown here, and it's called meridian time difference, where this was the time difference in hours. The next step is to get meridian time difference, and that's where we take the 4.6 hours and round it either up or down. In this case, we round it up since it's greater than 4.5. We round it up to 5, as shown here, and that gives us the 5th time zone west of Greenwich. And this is noted here, round up or down to a whole number in standard mathematical fashion, that is, decimals of 0.5 or greater are rounded up, and decimals less than 0.5 are rounded down. And the sign of MTD is positive for west longitude and minus for east longitude. So now to compute Greenwich Mean Time, we have to take our zone time and add the meridian time difference, the 5 meridians from Greenwich, and get 1328.38 as the Greenwich Mean Time corrected. And that is shown on our calculation right here, where we take our zone time, 0828.39, and we subtract 1 second for the watch error correction, and we add the 5 hours for the time zone difference, and we get a corrected Greenwich time of 1328.38. Then our next step is to calculate the observed altitude. Now, using the sextant, we got HS, the sextant altitude. And if you recall our previous discussion, that we have 2 corrections first off to add to that, and these corrections have nothing to do with the sun. They have to do with the sextant and you in the boat, but nothing to do with the sun. And those 2 corrections are the index correction, and we talked about taking that when we looked at the sextant, and we have the dip correction, which has to do with the height of eye, with your height of eye above the sea level when you took a shot. Okay, so let's first go to index correction, and looking at the calculation here, we see that this says index correction plus 1.7. Well, we get the index correction from the index error. The index error was 1.7 minutes off the arc, and therefore we add it back in. We make it plus 1.7. That corrects for the index error. And now we have to go to the dip correction, and let's look at this discussion here. And the dip correction to the sextant altitude is based on your height of eye, HE, at the time of observation. And our height of eye was 8 feet above the water. So we're going to use that to look up the dip correction. Before we look it up, let me show you a little bit about what the dip correction is. Sextant altitude of the sun, and here is your location. Here is the horizon that you see when you look out past your boat. And if your eye is at the water level, this would be the sextant altitude that you would be reading to the bottom of the sun as compared with your visual horizon. But your eye is not at the water level. It's actually 8 feet above the water level, as shown in this diagram. So here is your eye here. Here is the required horizon stemming from the surface of the water. But since your eye is 8 feet up above the water, your actual visual horizon is this red line here. Okay? And you can see that if you shoot the sun from this horizon, that HS is going to be larger than the required HS. So you see here that going from this visual horizon up to this line to the sun is the HS that you actually took with your sextant. But this is the sextant altitude that you want to get right here. So the observed HS is always larger than the required HS, and the distance that your eye is above the water will change the angle of this visual horizon and therefore change the HS. So what we want to do is look up what the dip correction will be for different heights of eye. And let's look at that. So this part of the calculation tells you that your dip correction is shown on page C-4. That's page C-4 in Appendix C, and it comes out of the Nautical Almanac. So let's look at that, C-4, and that's shown here. So the altitude correction table for 10 degrees to 90 degrees apparent altitude for the sun, the stars, and the planets. And it's broken down into 3 sections. One is a set of numbers for the sun, numbers for the stars and planets, and then the dip correction, which applies to whatever body you're shooting, because remember, the dip has nothing to do with the body that you're shooting. It has to do with you and your sextant and your boat. Okay? So let's look at this table, and let's come down here a little bit further on the right hand side, and you see here feet and minutes, very, very tiny minutes written in there. Okay? So if your height of eye is 2, 4, 6, 8, or 10 feet, these are the corrections for dip. And this is a minus sign, minus 1.4, minus 1.9, and so forth. So the dip correction for 8 feet, which we have, is minus 2.7. And you see that here, minus 2.7 from appendix page C4. So you have HS, and you add to that 1.7 minutes for index correction, and you subtract 2.7 minutes for dip correction. And with that arithmetic, you then get the apparent altitude, 27 degrees, 14.9 minutes. Okay, our next step here in paragraph number 10 is to use the HA that we just calculated to look up the altitude correction AC1 in the Nautical Almanac as shown on pages C4 or C5. And let's just note here that we have AC1, the note here on the right hand side says page C-4 in order to get that, and AC2 page C-6. So let's go back to the paragraph. And this says in sample number 4, HA equals 27 degrees 14.9. Use the 10 to 90 degree table on page C4. In the left-hand set of columns marked sun, choose the correct month, which is November, and this will put us in the leftmost column marked October to March. In these columns, choose the lower limb column. In the apparent altitude column, find the two numbers which bracket your HA, the 27 degrees 14.9, and read the altitude correction. Thus, since your HA of 27 degrees 14.9 is bracketed by 26 degrees 36 minutes and 27 degrees 52 minutes, read AC1 as 14.4. And here we are on page C4. So we have the left-hand group of columns marked sun, and since our date is November, our month is November, we choose the leftmost set of columns here, October to March, and below that you see three columns: apparent altitude, lower limb, upper limb. Now we took a lower limb shot, so we're going to be using the middle column here to get the AC1 correction. We're going to follow down the apparent altitude as we just read in the text, and we see that our HA of 27.14.9 is bracketed by 26.36 and 27.52. So our correction is 14.4 plus, and that plus is a plus, and this minus is a minus. So AC1 is plus 14.4. And let's go back to our discussion here. We looked up 14.4. And on the calculation, we see here 14.4 that we entered in for AC1. Okay, our next step is to look up AC2, and as shown here, we're going to find that on appendix page C6. So let's go back to the text and read the instructions on this. And this is in paragraph 11 here. And AC2 is based on the temperature, the atmospheric temperature, and the barometer reading. It's not a very large correction for most conditions, like summertime conditions of sailing. So from sample problem number 4, appendix page C6, which is the altitude correction table for temperature and pressure, enter the top portion of this table with temperature 73 and barometer 1033 millibars and find the sloped column marked H. Follow the sloped column down to the lower portion of the table for HA 27 degrees 14.9 and find the refractive altitude correction AC2 equals plus 0.1 minutes, not very much. And here we are in C6, this table, altitude correction table, and we see across the top degrees Fahrenheit, and on the left-hand side we see pressure in millibars. So our temperature, our air temperature is 73 degrees Fahrenheit, and we take that point and drop a line straight down, not on an angle. And then 1033 millibars, we project a line straight horizontally, and where the two intersect, that puts us in sloped column H. We follow that column down to the lower half of the table, to the column H here, and in the very left-hand column we see apparent altitude, and that apparent altitude is in degrees and minutes. So we follow that down to this area here where we see 25, and that's degrees, and 30 degrees. Well, our HA is 27 degrees 14.9, so it's actually closer to the 25 than it is to the 30, because 27 degrees 30 minutes would be the midpoint of this. So we're actually closer to the 25, and I project that over, and that gives me a correction of 0.1 minutes. And this column is in minutes, as you see it up here minutes. Okay? And let's go back to our calculation page. And we say here AC2 is plus 0.1 minutes. Okay? And we add those up and we get an HO, the observed altitude, of 27 degrees 29.4. So now we have a corrected Greenwich time and a corrected altitude for the sun. So now let's go to the next section, which is the ground position of the sun. And that's measured in 2 dimensions, GHA and declination. So let's see what the text is saying about this. And this says, look up ground position. All right. So this says, next, look up GHA and DEC information from the daily pages of the Nautical Almanac. These numbers will define the GP of the sun at the precise time, GMT, of your observation. Track the following steps in sample problem number 4. So looking at this, using the date November 5th, 93, and the whole hour of GMT, which is 13 hours, look up the Greenwich hour angle, GHA, and the declination, DEC, and the D factor, little d factor, for the sun in the daily pages of the Nautical Almanac, as shown on page C15. So that's the daily page. Give a plus sign to the D factor if DEC is increasing from the 13th to the 14th hour, and give a minus sign if DEC is decreasing between the 13th and 14th hour. In our case, it is increasing, and here's the results of our lookup, but let's look at the table. Here we are. This is November 3, 4, and 5 in this one page. It covers 3 dates. And you see down the left-hand column, you see GMT, and you see the date of 3, the 3rd of November, Wednesday. The next is November 4th for Thursday, and the bottom one is November 5th for Friday. And let's look at the legends at the top. So across the top we see sun, GHA and DEC, and then we have moon, and then we have sunrise, sunset, and moonrise, moonset data, which we'll talk about later in chapter 3 actually. So under sun, we see GHA in degrees and minutes, declination in degrees and minutes. And when you look at the declination, you see this south 15. That means south 15 degrees. Let's come down to November 5th, where I've got these circled. And they don't print the degrees, south 15 degrees, on every line. They skip every 6 lines. But this south 15 degrees applies to every line, even though it only is printed on every 6th line. And our whole hour of 13 is shown here. And next to that, we see the GHA of 19 degrees 05.6 and the declination of south 15, 46.8. And we also see that the declination minutes are increasing as we come down the page. Here you see 46.0, 46.8, 47.5, 48.3, 49. Okay, so they're increasing. So the little d that we're going to look up is a plus little d. And here's the little d for this column, 0.8. So it's going to be plus 0.8. So let's go back to our calculation. And here we see that information entered. For 13 hours, we see 19 degrees 05.6. And we see for GHA. And we see declination south 15 degrees 46.8. And a little d factor of plus 0.8. Now that's the whole hour. But the GMT was 13 hours, 28 minutes, 38 seconds. So we now have to look up the 28 minute, 38 seconds portion of this. And to do this, we're going to use appendix page C25, which also comes from the Nautical Almanac. And let's look at C25 here. And you see written up the top, you see 28M. That refers to 28 minutes for this series of columns. On the right-hand side, 29. That's 29 minutes for this series of columns. Well, we have 28 minutes and we have 38 seconds. So coming down the left-hand column here, we have 38 seconds shown here. And let's look at the legends at the top. And we have the sun and the planets, Aries, and the moon. And under sun and planets, which is the first column next to the seconds, we see for 38 seconds, we see 7 degrees 09.5. And that is 28 minutes, 38 seconds, 7 degrees 09.5. And let's go back to our calculation, and we see that entered here, 2838 under GHA, we have 7 degrees 09.5. Now we have to deal with the little d, this little interpolation factor. And we go back to that page C25, and on the 28-minute section of this page, we see these three columns which say V or D correction, and all three columns say that same thing. And then what's written in here is minutes. And in the first column, down the left-hand subcolumn, we have sequentially 0, 0.1, 0.2, 0.3, 0.4, etc., all the way down the page sequentially. The next column 6.0, 6.1, next column 12.0, 12.1. Okay? So to pick off the correction for 0.8, we look up here. This says V or D. Well, our D is 0.8, and 0.4 is the correction. And since 0.8 was plus, the correction is going to be plus. So back to our calculation, 0.4 is the correction. So let's go back to our discussion page, and that is all described here. The 13 hours, 1905.6, south 15 degrees 46.8, and the little d factor 0.8 plus. We looked up for 2838, and we have 7 degrees 09.5. And we looked up for the 0.8 d factor and found 0.4. And we add up all that arithmetic, and we get the Greenwich hour angle and the declination of the sun's ground position. GHA 26 degrees 15.1 and declination south 15 degrees 47.2. And we see that written here. Our next step in this process is to calculate the longitude distance to the sun's ground position, the longitude distance in degrees. And that's called local hour angle. And local hour angle is the angle west of us that the GP is located. So the GP is located to our west by the number of degrees defined by LHA. Reading paragraph 14, local hour angle LHA is the angle that the GP of the sun is west of your position, as shown in the following figures, 122A and B, and it's computed as follows. LHA equals GHA, which we just looked up, minus longitude. And LHA is the angle that the sun's GP is west of us. In the western hemisphere, longitude is plus. In the eastern hemisphere, longitude is minus, as we do these calculations. Now what I'm going to show you here are some diagrams to illustrate LHA. The numbers shown here are not the ones from sample problem number 4. These are just to illustrate the concept of LHA. So when I look at this diagram on the right here, I see the Earth. I'm looking down from the North Pole. Over here I have Greenwich, and Western Hemisphere is going this direction. And for this example, the GHA is 90 degrees to the sun's GP. Our position, our longitude, is 70 degrees to the west. Now remember, LHA is the angle that the sun's GP is west of us. So since it is 90 degrees west and we are 70 degrees west, it's therefore 20 degrees west of us. And therefore the LHA is 20 degrees. You don't have to specify west because LHA is always a westerly angle. So that's where the LHA is to our west. Let's look at the next example shown here. And in this case, again, we're looking down on the Earth from above the North Pole. Here's Greenwich, England. Here is the sun and the sun's GP right here. And that is, follow this arrow around, GHA of 200, Greenwich hour angle of 200, from Greenwich to the sun's GP. And we are located in the eastern hemisphere in this example, 80 degrees to the east. So follow this around from our position all around westerly is 280 degrees LHA. Well, you look at the sketch and you can see 200 GHA and 80 degrees for our longitude. So 80 plus 200 is 280, and that's LHA, west of us. That simply illustrates LHA and what LHA is. So let's then go down to this next topic. And this says calculate your assumed position. And let's read this. Next, establish an assumed position, AP, by adjusting the minutes of your DR longitude to produce a whole number for LHA when the subtraction of equation 7 is performed. This is necessary so that you can use the site reduction tables, which only list whole numbers of LHA degrees. Now, before we do the correction of longitude, since I'm going to be subtracting a longitude of about 69 degrees from 26 degrees of GHA, I'm going to add 360 to the 26 GHA and get a GHA of 386.15.1. Now I can subtract a larger number, like 69 degrees, from 386. But how did I get to 69.15.1 in order to do this? Well, there's two parts to that. First off, let's look at the dead reckoning longitude. And here it is 68 degrees 59.0. And let's go back to our discussion in the text and look at this. So we had DR longitude 6859.0, and we had the GHA of, after we added 360, of 386.15.1. And we're subtracting an assumed longitude, that's what the A means, of 69.15.1. We arrived at this number in two steps. First off, we took the 15.1 to be the same 15.1 as the GHA. So whatever the GHA minutes are, we assign that number of minutes to the assumed longitude. As we just read in the text, that the reason for that is so that when you subtract assumed longitude from GHA, you'll get an LHA with 0 minutes, because the table for LHA does not include minutes. It only includes whole degrees. And that's described here. Choose the A-Launch minutes to equal GHA minutes 15.1 so that the A-Launch subtraction will produce a whole degree of LHA, which is needed for lookup in HO229. So that's where we got the 15.1. Now let's look back at the calculation here, sample number 4. And we see up top for longitude 68 degrees 59.0, we want to choose the assumed longitude to be within plus or minus 30 minutes, plus or minus a half a degree, of the DR longitude. Well, here's your DR longitude, 68 degrees 59.0, so I'm going to form a bracket plus or minus 30 minutes on each side of that. And here's that bracket, 6829.0, which is 59 minus 30 is 29, and 6929 is 30 minutes greater than 6859. So here's my bracket, 6829 to 6929. I'm going to use that bracket to determine the degrees for the assumed longitude. Okay, so that's the bracket that we just determined based on our dead reckoning and plus or minus a half a degree on each side of it. So I have to decide whether I'm going to use 68 degrees or 69 degrees or 70 degrees. If I choose degrees 68, that will give me 68.15.1 for the assumed longitude, and that will be below this bracket, which is the bottom end is 68.29. I would have 68.15.1. That would be outside the bracket. If I choose 69.15.1, that will be inside the bracket. And if I choose 70.15.1, that will be outside the bracket on the top side. And that's described here in this writing. And choose the A-Launch degrees to produce an A-Launch within the range of plus or minus 30 minutes of the DR longitude. For example, our DR longitude is 6859.0 minutes, and the plus or minus 30 range is bounded by 6829 west and 6929 west. Thus, choosing A-Launch degrees of 69 produces an A-Launch of 69.15.1, which falls within the required range, whereas 68.15.1 or 70.15.1 fall outside of the required range. So I make this subtraction now, and that gives me an LHA of 317 degrees with no minutes. That's LHA. And let's go back and look at the calculation. And here we are, shown here, assumed position, A-Launch 69.15.1, LHA 317. And then our next step, I'm going to skip down here to paragraph 16. Choose assumed latitude, A lat, as the nearest whole degree to your DR latitude. So A lat is 31 north. And if we look at our DR latitude, we see it's 31 degrees 25.7, which is less than half a degree. So therefore, I'm going to round that down to 31 degrees of latitude. That's shown here. And let's go back to the text for a second. And that's shown here. The next step now is to look up the sun's calculated altitude and azimuth. Because you now have 4 pieces of data shown in figure 123, and we'll look at that in a second, that define your position in relation to the sun's GP. All right, and let's look at this figure 123. So you have assumed latitude and assumed longitude, which define our assumed position. We have the GP of the sun, okay, and we have the LHA, which is the westward angle from our longitude around to the GP of the sun. which was 317 that we just calculated. And this circle represents a spherical Earth, and the 3 points shown on here are a spherical triangle on the surface of the Earth, bounded by the 3 points, the North Pole, in this case, which is the closest pole, the assumed position, and the ground position. And all of these arcs are parts of great circles which are centered at the center of the Earth. So these are the 4 pieces of data that we need to look up the calculated altitude and azimuth. The LHA, the ALAT, the declination of the sun's GP north or south of the equator, and the polarity of ALAT and DEC. That is, are they in the same or different hemispheres, north or south? Looking here, we see that declination is in the southern hemisphere, south, and latitude, our assumed latitude, is in the northern hemisphere, north. So our polarity is different or contrary. And the table that we're going to look up says contrary. There's another table that says same. If they're in the same hemisphere, either both north or both south, that's called same. If they're in different hemispheres, north and south or south and north, then it's called contrary. And we're going to look this up in appendix page D19. And that page comes out of the site reduction table. So let's go back to our text and look here. So we have the 4 pieces of data, and we're going to go to HO229, the site reduction tables, in order to calculate HC and ZN using the 4 pieces of data. And remember that HC is the angle that the sun would be above your horizon at the instant of observation if you were located at your assumed position. And Zn is the bearing or azimuth from your assumed position to the sun's GP at the instant of observation in degrees true. And we'll use HO229 to do that lookup. And here are the actual numbers that we're going to use for that lookup. LHA 317, ALAT 31 north, declination south 15 degrees 47.2, and contrary. These are different hemispheres, ALAT and declination. So let's go to D19, and you see this says contrary. That's for different hemispheres. Our LHA is 317. Our assumed latitude is 31 degrees, and you see 30, 31, 32, etc. And these can be either north or south, depending on what hemisphere you happen to be in. And down the left-hand column, you see declination in degrees. Now, that's only the degrees portion of declination. Remember, the declination was 15 degrees 47.2, and this is degrees. So we're coming down that column to the 15-degree line, and I look at the top here of under 31 degrees latitude, and I see HC, D, little d, and Z. And little d is simply the difference between one line to the next. So on the 15-degree line, I see my HC is 28 degrees 10.7. My little d is minus 45, and that minus 45 is simply the difference between 28.10.7 and 27.25.7 is minus 45, because we're going to use that as an interpolation factor to figure out our minutes of declination as a next step. And our z is 131.6. So let's take those numbers first off and transfer them to sample problem. And here's the numbers that we just looked up. For 15 degrees, 28 degrees 10.7, the interpolation factor being minus 45.0, and the z being 131.6, which I round off to 132. But let's go and define what z is. And you see this triangle that we talked about a few minutes ago, and z is the internal angle of that triangle between the meridian from AP to the North Pole, and that is a great circle laying along a meridian, and the azimuth from the AP to the GP. So z is that internal angle of that triangle. And then depending on some other factors, you're going to convert that z to a zn, and I'll show you that in a minute. And we have done this. We had this discussion here. So we found the LHA of 317 degrees in HO229 on appendix page D19, where the names of latitude north and deck south are contrary to each other. If the names were the same, both north or south, you would use the same page. On page D19, find the latitude 31 degree column, which we just did. Follow this column down to the row marked declination 15 degrees and find the following data, which we just looked up. And we transfer that to our calculation page. Now, HC is the calculated altitude of the sun for deck equals 15 degrees, but the actual deck is 15 degrees 47.2 minutes, and we need to account for the effects of this additional 47.2 minutes of deck in the final value of HC. So we're going to do this simply by arithmetic with this interpolation factor. And as noted here in this yellow box, the little d is simply the difference from one line in the table to the next line. And to find the HC increment resulting from this additional 47.2 minutes of deck, calculate as follows. HCI, the HC increment, is deck minutes, which is 47.2, divided by 60 minutes per degree, times the little d, which is minus 45. 47.2 times minus 45 over 60 equals minus 35.4. So that's a subtraction from the HC that we looked up for the whole degrees. So what we just did here then is that we took that minus 35.4 for HCI, we put it into our calculation of minus 35.4 here, and that was for the declination minutes of 47.2. We did that subtraction and got 27 degrees 35.3, and let's look back again at our text, and that's shown here, that arithmetic. Okay, so that gives us HC, the calculated altitude. That would be the altitude of the sun above your horizon if you were located at the assumed position when you took the shot of the sun. The next step is to compute Zn from Z as shown below. And these are the equations for doing this. And depending on where you're located, north or south, and what the LHA is, what the value of the LHA is, determines which of these four formulas you use. If the AP, the assumed position, is in the northern hemisphere, and if LHA is less than 180, then Zn equals 360 minus Z. If LHA is greater than 180, then Zn equals Z. Well, we are in the northern hemisphere. Okay, that's our assumed position. And our LHA is 317, so it's greater than 180. So therefore, we're going to use Zn equals Z. But let's read the rest of these formulas. If AP is in the southern hemisphere, and if LHA is greater than 180, then Zn equals 180 minus Z. If LHA is less than 180, then Zn equals 180 plus Z. So our Zn equals Z. So let's go back to the calculations here. And you see Z equals 132. Therefore, Zn equals Z equals 132. True. Our next step then is to calculate the intercept, that is the distance from the assumed position to your observed line of position. And to do that, we're going to take the difference between HO and HC. Well, right here you see that the difference is the degrees are the same, the minutes are different, so 35.3 minus 29.4 is 5.9, and we have this word here, away. Well, let's go back and look at the text again and see the explanation here. I'm going to skip all the way down to here. Calculate distance from assumed position to LOP. The intercept I is the distance in nautical miles between your assumed position, AP, and your actual line of position. And from sample problem number 4, does this arithmetic and shows 5.9, and it says away. Well, whether it's away means it's in the away direction from the ground position. If it's in the other direction, it'll be called toward. Okay? So let's read this. This results in minutes of arc which equal nautical miles, since we're on a great circle. If HO is larger than HC, then I is designated as toward the GP, and is plotted towards the GP in the direction of the ZN. The term homo-tow means if HO is more than HC, plot the intercept towards the GP, homo-tow. And the opposite is if HO is less than HC, then I is designated as away and is plotted in the reciprocal direction of the ZN, or the away direction from the GP. Now, what in the world does all that mean? So let's look at figure 125. And here we have the sun and the sun's GP. We have the assumed position on this red circle. And we have the line of position on this blue circle. The blue circle is defined by HO. And the red circle, AP, is defined by HC. Now, HO, in this case, is more than HC. HO, the LOP, is closer to the GP, so this angle is greater than the HC angle. Therefore, the intercept will go from the AP toward the GP to the LOP. So let's look at another diagram to clarify that. This is the case of, here's the sun, here's the GP. HO angle is greater than HC angle, homo-tow. So here I have HO is a greater angle than HC. So the intercept is plotted from the AP towards the GP in order to define LOP. And the opposite of that, which is what we have in sample problem number 4, HO angle is less than the HC angle. Therefore, the intercept is plotted in the away direction from the GP in order to define the LOP. So here we are. HO is less, away. HO is more, towards. Okay? So let's go back here, and we see that. And let's go back to our calculation, and we see that HO is less than HC. Therefore, we define this 5.9 as being away from the direction of the GP. Now, the next part of this tale is to plot your LOP. And this is shown in figure 126 on the next page. And let's go back to the words in the text first, and then we'll come back to this picture. So your line of position is plotted as shown here. Locate your assumed position by plotting A lat and A longe. From your AP, draw in ZN, the bearing in true degrees to the sun's GP. From your AP, measure the distance in nautical miles along the ZN equal to the intercept length. If I was toward the GP, then plot this distance in the direction of the azimuth ZN. If I was away from the GP, then plot in the opposite direction. Draw a line through the end of I perpendicular to ZN. This is your line of position, LOP. Mark it as sun with the ship's time of observation in hours and minutes, dropping the seconds, in this case sun 0828. And that's all shown here. So we look at our plot and we see latitude, longitude here 69 degrees, 70 degrees west, and here's 31 degrees north, okay, because here's 32, here's 31, and our assumed position was 31 degrees north and 69 degrees 15.1 longitude west. So here's 69, here's 70, 5, 10, 15.1, and that marks the assumed position. We plot our azimuth from the assumed position at 132 degrees, which was the ZN that we calculated. But we want to plot in the away direction, so the 5.9 miles is plotted opposite to the direction of the ZN. 5.9 miles in the away direction, and then we draw a line perpendicular to that, perpendicular to the azimuth line, and that is our sun LOP. And it's marked sun 0828 with hours and minutes. Okay, so that's it.
Well, I hope you found something useful in this video, and I thank you for watching.